Take a normal apple, hold it in the air, and let go. We all know the rhythm of this descent, a predictable part of life. This constant downward tug is our baseline gravity, a force we measure as 1g. But imagine what happens to that motion if you multiply this everyday force by 200 billion. At this magnitude, the math we use to predict a falling object reaches a limit. The rules of our low-gravity world cannot describe what happens next. This environment isn't a theoretical exercise. It exists in the form of an object called a neutron star. It reveals that the stable, predictable gravity we feel every day is actually a rare exception in a much more violent universe. To understand exactly how a single star generates that much pulling force, we first have to look at the scale of our own sun. The process begins when a massive star, significantly larger than ours, exhausts its internal fuel supply. Without the outward pressure of nuclear fusion to hold it up, the star's entire mass violently collapses inward under its own weight. This forces an object with more mass than the sun into a sphere just 12 miles wide. Because none of that original mass was lost, the density of this 12-mile ball is pushed to a limit that is difficult to visualize. We can grasp it by imagining the immense weight of a single teaspoon of this material. On Earth, that teaspoon would weigh over 1 billion tons. To reach that billion-ton mark, you would need to take the weight of the Great Pyramid of Giza and multiply it by hundreds. This massive compression acts as an engine, turning the star into a concentrated gravity generator unlike anything else in existence. While the internal density is staggering, the absolute ultimate test of physics happens in the space immediately surrounding the star. Merely standing near the surface would result in instant obliteration, as the gravitational shear is too strong for any physical structure to hold together. If we revisit our falling apple and drop it from just a few feet above the neutron star's surface, the results change. The gravity pulls the object down so violently that it hits the surface at 4.3 million miles per hour. This force is so extreme that it even dictates the behavior of light. The gravity is powerful enough that it physically bends light waves around the 12-mile sphere. Because light from the far side of the star is curved back toward you, you would be able to see the front and the back of the star simultaneously. By forcing matter to these speeds and warping the physical path of light, a neutron star proves gravity can overrule the standard laws of motion and optics. Pulling back from this 12-mile sphere allows us to see gravity for what it really is across the wider cosmos. On Earth, we think of it as a gentle tether that keeps our world in order. But in the deep universe, gravity is a ruthless sculptor, capable of warping the very fabric of space. These stars function as the universe's most extreme laboratories, proving that the physics we see on Earth are only a specific, low-energy subset of how the universe actually operates. The cosmos is physically uncompromising. Does the mind-blowing physics of the universe fascinate you, or does it scare you? Let us know below.